In this section, we're going to take a look at the graphing process. Specifically, we'll look at how to plot points, how to determine solutions from an equation, how you can start graphing those equations, how you can use the x and y intercepts to make a little bit more accurate graph, and finally, how you can use all of that information to start graphing some functions. When we graph equations or functions, we use what is known as a Cartesian coordinate system. It's basically two number lines that have been stuck together at 0. So the one that is horizontal is known as the x-axis, and the one that's vertical, straight up and down, is known as the y-axis. Now, we basically take ordered pairs and put them onto this Cartesian coordinate system. And the way you read this is basically by taking an x value and a y value. So here below I have an example like 2, 3. The way I put this on the graph is first I find 2 on the x-axis, and then I find 3 on the y-axis. And where those two intersect, I go ahead and I put a point. So notice how this point is at the intersection of where x equals 2 and where y is equal to 3. All right, let's go ahead and grab another one. Here I have the point -3, 5. So again, I'd find -3 on the x-axis, and I'd find 5 on the y-axis. I'd find where both of those intersect, and I'd go ahead and I'd put a point. Now, an equation basically tells us how the x and the y values are related. So when I see something like 5x minus 3y equals 12, I can think of it as a relationship between x and between y. Now, what we basically want to do with this equation is have it generate a few different points for us. But one thing you might have in your mind is, well, how do you know the point really did come from that equation in the first place? Well, fortunately, we can always check just by plugging it in. So for example, here I have the point 3, 1, and maybe I'm curious to see whether it did come from my equation here. Well, if I plug in the 3 for x and the 1 for y, I can see that indeed everything does work out nice. So what this really tells me is that that point 3, 1 is a solution of the equation, or maybe another way I could say it is that the equation produces the point 3, 1. All right, let's try this again with the point 0, 4. Again, imagine plugging in the 0 for x and the -4 for y. Does it balance out? Do you get a true statement? You'll notice that this one also works out just fine. So I can say that this is another solution of the equation. So in general, really you can do this with any type of equation if you have a point. Imagine just plugging it into the equation and see if you get one of those true statements. If it does, then you know you have a solution, or you have some sort of point that came from the equation that you can put on your graph. Let's do some quick practice right now by determining whether the following points are solutions of the equation. If you want, you can pause the video at this point and end up testing out each of the points one by one. It turns out that the first one is a solution of the equation. Again, imagine plugging -9 in for x and 0 for y. And you'll see that you get an expression 18 equals 18. Now, the other two are a little bit more complicated equations. And it turns out that when you try and plug in 1, 7 into its equation, that one doesn't work out. So I know that 1, 7 did not come from that one. 0, 5, when plugged into the bottom equation, works out good. I get 4 equals 4. So only the first and the third points are solutions of their equations. Now that we know a little bit more about plotting points, and we know whether we can determine if a point is a solution, we can put these two ideas together in order to graph an entire equation. The idea here is that we will take an equation and have it generate lots and lots of different points for us. The process for doing that is basically choosing a value for one of the variables, and then going through the solving process to see what the other variable must be. This basically generates lots of ordered pairs, which we then go ahead and put on our graph. Now, the advantage of this system is it's actually a fairly easy thing to do, going through, plugging in values, and solving for the other variable. The downside is that if we don't use very many points, we might not get a very good picture. So one thing I always like to tell my students is that the more points you generate, the more accurate your graph will become. So let's see this process in action with the following equation. 2x plus 3y is equal to 12. So what I'm going to do is basically choose a whole bunch of different values for x. Now you might be wondering, where did all of these values come from? Well, when I choose some values, I like to choose a few that are negative, a few that are positive, and 0 seems to be usually a pretty good choice. so I have a pretty good mix. But you could even choose different points for your x. You might choose something like -7, -3, -2, and then throw in 4, 6, and 7, just as long as you have a good mix of some different values. Now each of these x's, you imagine plugging them in for x, and then going through the solving process to see what y has to be. To save some time, I'll show you of the different values that I already got for y. So when I plugged in a -3, I got that y was equal to 6. I plugged in a -1, I got that y was equal to 4 2/3. Now every single row in this table here essentially represents a point that I'll go ahead and I'll put on my graph. So remember, you find the x point first and you see where it intersects the y. Now this basically gave me 5 different points that I put on my graph. And after putting those 5 points on there, I could see that it starts to look kind of linear. So the next step is I go through basically filling in all of the dots and draw a straight line through all of my points. The line itself represents the graph of the entire equation. Now when you go through this process, you may end up graphing lots of different points, or maybe only a few. Remember that the more you graph, the better or more accurate your picture looks like for the equation. The good news is that if you can be sure you're graphing a line or a linear equation, then really you only need 2 different points on your graph. Now, 2 really good choice for points, if you're only using 2, are the x and the y intercepts. This is basically where the graph of the equation crosses the x-axis and where the graph will cross the y-axis. The reason why these are really 2 good points to choose is that either x or y will end up being a 0. Now, it's also a good idea to find the x and y intercepts for other types of graphs, even if they're not lines, but sometimes you may have to use a little bit more advanced techniques in order to figure out exactly where they cross the x and where they cross the y's. In addition, you may also have to find some more points other than just the x and y intercepts to get a more accurate picture. So to show you an example of using the intercepts, I'm going to graph this equation, -5x plus 2y equals 20. Now it happens to be a line, so these 2 intercepts I find will be all that I need in order to graph it out. Now rather than going through and finding a whole bunch of different values for x, plugging each one in and solving for y, I'm basically going to use 0 for x and 0 for y and use these as my 2 points. Now the first one that we end up finding, when x is equal to 0, that will be our y-intercept. And the next one, when y is equal to 0, that will be our x-intercept. Okay, so let's do this one at a time. Imagine plugging in x equals 0 into the equation. Now when you do so, you'll notice that the -5x term, it drops away entirely, and so you just have a much smaller equation, 2y equals 20. Solving that will give you that y is equal to 10. Now go ahead and plug in y equals 0 into the equation and solve for x. You'll quickly find that x must equal -4 in that case. So here I have 2 points that I can now put on my graph. Now the first one, 0, 10, it ends up on the y-axis, and the next one, -4, 0, ends up on the x-axis. Now since I can be sure that this really is a line, I draw a straight line through both of those points. And there you go, there's my entire graph of the equation. So we've graphed out a few different equations now and seen how the intercepts can really help us if we have just a line. And you might be curious, well, how does all of this apply when I start graphing a function? Well, the good news is it's really the same process as before. You'll end up choosing lots of different values for x and then seeing what your output or the y values need to be. You may notice that with functions, the notation is just a little bit different than you're used to. For example, here I have a function f of x equals 3x plus 7. And when I go to plug in an x value, like a 4, it's going to look something like this, f of 4. Now, don't worry, essentially on the right side, we're still going to replace that x with a 4 as well. And essentially, I'll keep working with the right side of that function, the 3, the 4, and the plus 7, and try and simplify it as much as possible. What I'll end up with in the end is that f of 4 equals 19. And the way you want to read this is that 4 is essentially your input, that was the x value we used, and 19 is our output, that will be our y value. Alright, let's put these ideas together and graph the following function. F of x equals x to the third power plus 1. For this one, I'm going to pick a whole bunch of different values for x. And again, I chose a few that were negative, a few that were positive, and I put 0 in there as well. For each of these, I'm going to take them and plug them in for x. So let's start with the first one. If you take negative 2, you cube it, you would get a negative 8, and then plus 1 would give us a negative 7. So that's going to be the output. Take a negative 1, plug it in as well. So negative 1 cubed would be a negative 1, and then plus 1 would equal 0. Now, after you do that for the rest of the points, you know all of your outputs. So we're going to treat the inputs as our x values and the outputs as our y values and plot each of those individual points. Now, just like before, the more points I do this with, the more accurate my picture becomes. Now, with this one, it looks like I got a little bit of a wave in the middle, so I'm going to try and connect the dots as best I can. And the line represents the graph of the entire function.